So we're going to continue studying waves by looking in particular at sound waves, which are the prototypical example that we use for a longitudinal wave. And longitudinal means that they go side to side. They're also called compression waves. We can still describe speed of sound as velocity equal to wavelength times frequency, because sound waves are waves after all, but the speed of sound actually changes depending on the temperature in the medium that you're traveling through. So the speed of sound in air, we typically say, is 331 meters per second times the square root of T divided by 273 Kelvin. And now this T isn't actually the period, which we've been working with in previous chapters. This big T stands for temperature. And we can keep this straight because we need a velocity. I have meters per second here. I have Kelvin in the denominator, so that means I need Kelvin in the top so that they cancel out. And I get the dimensions that I need. So, a little bit more about sound. We have biologically evolved to be able to hear sound, and this concept of hearing is actually how we perceive sound. And humans have a very specific set of frequencies that we can actually hear. So we can hear sounds between frequencies of 20 all the way up to 20,000 hertz. Another way that we can think about frequency is kind of thinking about pitch. So sometimes something sounds higher pitch, sometimes something sounds lower pitch. That pitch represents the frequency. And the intensity of the sound shouldn't be confused with the pitch. The intensity is kind of how loud the sound is. This is loudness. And this intensity of a sound wave is going to be equal to P divided by A, where P is the power of your sound wave, and A is the area that your sound wave is spreading out over. So the units of intensity are going to be equal to the units of power, which are watts, divided by the units of area, which are square meters. We also have other equations similar to pressure that we can use to calculate intensity. So another intensity equation for intensity of sound is change in little p squared over 2 times rho times v sub w, where delta p, the lowercase p, is a pressure amplitude. So that's how much pressure your sound wave can apply. Rho is equal to the density of the medium that you're traveling through. So that could be sound waves traveling through air, could be sound waves traveling through water. The density of the medium would be the density of whatever you're traveling through. And v sub w would be equal to the speed of sound in that medium. There is one other unit that we typically use to talk about sound, unit of decibels. So we represent that with the Greek letter beta. That stands for decibel, or decibels. So the sound intensity in decibels is 10 times the log to the base 10 of I, the intensity, over I naught, some threshold intensity, where we typically take I naught, it's going to be equal to 10 to the negative 12 watts per square meter. So this is the threshold of hearing. It's going to be the lowest intensity that you can actually hear with your own ears. Now, other interesting things happen with sound, not just decibels, not just loudness. The most useful characteristic of sound is typically something we call the Doppler effect. So this is an ambulance. When an ambulance goes by, the pitch seems to change. So this is a change in your frequency that's caused by motion. So the ambulance frequency isn't actually changing. It just sounds like it is because it's moving towards you or away from you. So if I have a moving source of sound, so this would be an ambulance actually moving, I can calculate how the frequency changes. The frequency that I observe, whatever I hear, is equal to the frequency of the source, so whatever the ambulance frequency is, times velocity of sound in whatever medium I have, divided by the velocity of sound plus or minus the velocity of the actual source of the ambulance. Now we could have the situation where I have a moving observer. If I have a moving observer, it's slightly different. Frequency that I observe is equal to the frequency of the source times the speed of sound in air plus or minus the velocity of the observer, all divided by velocity of the air. Now, all these variables we can keep in mind by saying Fs is the source frequency. Vs is the speed of source. Vw is the speed of sound in whatever medium you're inside of. Usually this will be air. Vobs is the velocity of the observer. And then the last thing we have to do is figure out when to use positives and negatives. So we have this little positive, negative. I have a positive if I'm moving toward the observer. I have a negative if I'm moving away. And you should check out the book to see how to combine these two if both your source and your observer are moving. Now, other aspects of sound that we should know. Sound behaves like waves on strings. And if we recall, these were standing waves. And where I can think about this is inside of a pipe organ in a church, and I can imagine trying to fit waves inside of a tube. So I'm going to draw a tube that's open on both ends. This is, again, like a pipe organ in a church. Now there's some rules for drawing waves inside of pipes. I need, if I have open ends, I need my wave to be open on those ends. So I can draw a wave that starts up at the top. I can't start in the middle because I have to start at the edge of whatever surface I'm having my wave put inside of. And I can draw my wave that goes down to the middle and then down to a minimum. And it's actually going to reflect. It reflects at the ends of this pipe, and it will reflect backwards. This is quite tricky to understand. You really need to read about it in the text to try to get some kind of frame of reference for how we're drawing these kinds of pictures. So the concept that we're doing here is fitting waves inside of a pipe. This is something known as resonance. It's interference of waves inside of a tube. Using the terminology from last chapter from waves, we know that the points where the waves are at maxima, we can give these positions the name of being antinodes. And positions where I'm at a minimum, We can call those nodes. We can calculate how many waves we can fit inside of this to get a frequency, and it turns out that the frequency inside of a pipe, F sub n, is equal to n times the velocity of the air inside of a pipe divided by 2 times L, where L is however long your pipe is. So I can use this to calculate frequencies that will happen inside of a pipe. This is when n is equal to 1, 2, 3, so on and so forth. So I can get the fundamental frequency, f sub 1 equals Vw over 2L. F sub 2 would be equal to 2 Vw over 2L, which would be Vw over L. So I can calculate the resonances that I have inside of this tube. I can do this for a tube that's actually closed on both ends too. So I take my tube, I draw it, and it's closed. So I'm going to shade those in. Now when I'm closed, I can't have antinodes. I can't have my wave be open. So I have to have nodes on both ends. So I can draw my wave going up and coming back down, hitting the center as a node. And then I can have it reflect and bounce back. And I can calculate what all the frequencies are for this resonance. It turns out the frequencies of each node will be n times V sub w over 4L, where L is once again still the length of this pipe. So this is how I can fit waves inside of pipes and establish resonances. So again, I recommend going back to the textbook and reading about these resonances a bit. The textbook can kind of make a little more sense, and they do some examples to make it more clear for you as well.